Okay, thank you so much for being here today. I cannot think of a better place to talk about science than Lake Observatory. It's absolutely gorgeous up here. I am Sanjana Curtis. Thank you so much for that beautiful introduction. I am a postdoc at UC Berkeley. And I'm very excited to talk to you today about one of my favorite topics in astrophysics, which is how the elements around us, the elements that make up our bodies, make up our world, came to exist. And so I'm gonna tell you a little bit more about myself and then we'll dive into it. So I am working in the field of nuclear astrophysics, which means that the goal of the field is to explain the origin of elements in astrophysical environments. So stars, supernovae, mergers of neutron stars, all of these exciting objects that we just heard about, those are the objects I study and I care about. I also work in the field of multi-messenger astrophysics, which is a big buzzword in astronomy. You may or may not have heard of it recently. It's just this really neat idea. Say there's some sort of astrophysical event, and you get one type of signal from it. Maybe it's photons. There's information that you can extract from those photons, but if you can also get from the same event a different type of signal, maybe it's neutrinos, maybe it's gravitational waves, then you can get complementary information from that other type of signal and you can put it together to create a more complete picture of the event than if you had only one type of signal. So that's multi-messenger astrophysics. That's what I do in order to understand how elements are created in the universe. Most of my work is theory and computation, so occasionally they let me out of the little room to come and hang out at an observatory with interesting people. But most of my time is spent sitting at a computer, coding up equations, running simulations, trying to understand what it is that my astronomer friends who use these wonderful telescopes actually observe. Okay, so with that, we'll get into all the nitty-gritty, but I wanted to start out with just the simplest question about our favorite star, the sun. What makes the sun shine? It's hot, so it shines, but what is actually generating that energy? And you may already know the answer, and it may seem obvious to you in this moment, but it actually took astronomers a little while to even formulate this question in a physically meaningful way. And that happened in the 1800s when we figured out some of the things about energy conservation and thermodynamics. And then we started asking, wait a second, the sun has been shining all this time. What is its energy source? And so initial ideas were quite interesting. People started out by thinking of just ways in which you generate energy here on Earth. So, you burn coal and you get energy. Is the sun burning coal? Is there some other kind of chemical reaction? So, hydrogen and oxygen combine to make water, that's a chemical reaction. Are there chemical reactions that could be powering the sun? Well, it turns out, not really. The amount of energy that you need to keep something like the sun afloat for a long time is truly enormous. And so, these ideas didn't quite work. There was another person who came up with this meteorite theory of the sun is constantly being bombarded by massive meteors, and they're delivering energy to the sun, and that's how the sun shines. Okay, so these theories didn't quite catch on. There was a really neat idea that came next, and this is the idea that gravitational contraction powers the sun. Okay, so very simple, very elegant idea. The sun contracts because of gravity. That generates heat, and that's powering the sun. And this remained a leading idea in terms of how the sun works in astrophysics for decades, up until the early 1900s, actually. This theory did have a small issue, which everybody was very well aware of. If the sun is powered just by gravity, so it contracts and heats and shines, the age of the sun that astrophysicists estimated was about 20 million years. Do you know the age of the sun? Do people know how old the sun is?
14 billion?
order of magnitude off, but yes, billions of years, yes. 4.6 billion years, we know now that the sun is so old, right? But even back in the day, they didn't know the exact age of the sun, but geologists and biologists had, were doing their own studies, and they were coming up with numbers that were hundreds of millions of years. And so there was this discrepancy between what astrophysicists understood how the sun works and the age that we were claiming, and what people in other fields were finding. And so this issue existed. Everybody was kind of like, oh, this is kind of a problem, but we don't have any better ideas at the moment, so let's stick with it. Okay, then comes the end of the 1800s, when Marie Curie and Pierre Curie, all these folks are doing very exciting work with radioactivity. And so we're beginning to find that these radioactive isotopes can decay and generate enormous amounts of energy. And so some astronomers figured maybe that's the energy source. Maybe the sun is just radioactive. It has a lot of radium, and the radium is decaying and powering the sun. Which I think was a very neat step that they took. However, this also turned out to not be the answer, because we can look for elements in the sun. The way we do this is we can take a spectrum of the light from the sun, and so you break down the photons as a function of their wavelength. You look at the spectrum. And if there are certain elements in the sun, you can see their fingerprints on that spectrum. So certain wavelengths will be absorbed, certain wavelengths will be emitted. So sort of the spectral fingerprint of the elements can be seen in the sun's spectrum. And of the known radioactive elements, we did not find any in the sun. So this kind of fell out of favor 1915 or so. Okay. Now, the 1900s were a very exciting time for physics, and we were making huge strides in nuclear physics. We were beginning to figure out that you can fuse elements, so you can fuse two hydrogen atoms to make a helium atom, and generate a lot of energy in the process. Einstein came in with E equals mc squared, so a small amount of mass can be converted into a huge amount of energy. And so as these strides in nuclear physics were being made, astronomers figured maybe it is nuclear reactions that are the energy source for the sun. So this idea was suggested already in something like 1920, but which nuclear reactions? Okay, that took another 20 years or so to really figure out. And so in 1939, Hans Bethe wrote two papers where he identified two nuclear reaction chains, both of which in some way burn hydrogen to make helium. And through that reaction, you can produce a lot of energy, and that energy goes into powering our sun. And thankfully, this also fixes the problem of the sun's age. The sun, powered by nuclear reactions, can live for a very, very long time. So all this went into understanding just our own sun, and we still don't fully understand it, right? So the sun is doing nuclear fusion. Other stars are also doing nuclear fusion. That is how stars shine. They're giant nuclear reactors in the sky. This was maybe 100 years ago-ish that we figured all this out. Since then, we've been working to understand stars a lot better, and to understand these nuclear reactions in stars a lot better. Okay. I also don't want to go on. If there's any questions, please just interrupt me and ask, because I would hate to leave people behind and continue on with the story. Anybody? Yes? Where did the hydrogen come from? Yes, that is a great question, and you will have the answer by the end of this talk. Very shortly, actually. Jake?
How much of the sun by volume is undergoing fusion?
By volume? Oh my gosh, that's a tough one. I don't know by volume, but I would say probably the inner core, which may be maybe like a half or 2 solar masses, something like that. Just the core of the star is doing the fusion process, where things are actually very hot and dense. Yeah. So it's not like all of the sun is fusing hydrogen. Okay. So stars do nuclear reactions, they make new elements. So now you might ask, hey, wait a second, there's helium on Earth. You're telling me the sun makes helium. Where did the helium on Earth come from? Did it come from a fusion process happening in a star? That brings us to the field of nuclear astrophysics. It is essentially putting together nuclear physics with astrophysics to understand how new nuclei form in the universe. What we study is called nucleosynthesis, the creation of new nuclei from existing nuclei. It's also the science behind the very famous Carl Sagan quote that we're all made of star stuff. This is the science that goes into making a claim like that. Nuclear astrophysics is also, in a very visceral way, related to our lives. It's the search for our cosmic origin story. Your body is made of elements. If you look at microplankton in the sea, maybe their body looks completely different than ours, but their skeletons, in this case, are made of strontium sulfate, actually. And as we go through this talk, you'll realize neutron stars had to die for that strontium to exist and for this creature to live. We have our own cosmic progenitors. We have our own cosmic parents, and we'll learn more about them as we go on. Okay, so let's get a little bit more specific with it. So you have to formulate the question of how did the elements come to exist in a more scientific way? So what do we do about that? We try to measure things. We try to measure the composition of the solar system. Now, most of the mass in the solar system is in the sun, so that's the main thing that we look at. We also look at stars, other stars in our galaxy, other stars outside our galaxy, and we try to measure as much as we can with respect to the composition of the solar system, the composition of the universe outside of the solar system. The thing that we're trying to explain is basically this figure. I will get into it. Don't worry about all the labels and so on yet. So by measuring the amounts of different elements in the sun, we've come up with this figure. And that's on the x-axis is the atomic mass of some isotope of an element. So it's not important, the details, but this is hydrogen, and this is heavier and heavier elements, gold and platinum and uranium. On the y-axis is how much of this stuff there is. So what this figure already shows you is there's a lot of hydrogen and helium in the universe, in the sun. As you go to heavier and heavier elements, there's less and less and less of them. It's harder to make those elements for various reasons. But essentially, this is the sort of pattern that we measure and the pattern that we want to explain. Now, could it be that everything was created right as the universe was born after the Big Bang? That is actually one idea that was suggested way back in the day. But now we know that the different elements in this pattern were not all created at the same time, were not all created in the same nuclear process, and were not all created in the same astrophysical event. So there's a lot of intricacy hidden here, which we will pull apart now. Okay. And once again, the way we are trying to answer these questions and what is really cutting edge in the field of astrophysics right now is this area called multi-messenger astronomy. And I already mentioned it a little bit, but here's a little bit more detail on that. So say 2 neutron stars merged somewhere in the universe. Neutron stars, when they merge together, they send ripples through the fabric of space-time. These are called gravitational waves. And in about 2015 or so, we began measuring gravitational waves from all sorts of merger events in the universe. So two black holes merging together, two neutron stars merging together, a neutron star merging with a black hole, these sort of events, we can now detect gravitational waves from them. And those gravitational waves carry information about what were the masses of the two objects that merged. Was the object a neutron star? Was it a black hole? Things like that. And so there's this fantastic observatory, the Gravitational Wave Observatory, called LIGO, and its sister observatory in Italy is called Virgo. These observatories keep an eye on the gravitational wave sky. Observatories that measure light, both ground-based like LIC and the observatories that are in space, they try to track basically everything from radio waves to gamma rays coming to us from the universe. Many astrophysical systems like supernovae, especially the very high energy ones, also produce these elementary particles called neutrinos. So neutrinos are coming to us from the sun, they're coming to us from supernovae. There are observatories that keep track of those neutrinos. And so IceCube, for example, is an observatory that measures the flux of neutrinos coming to us from the universe. And so when we have some sort of event, if we can get all of these pieces of information from it, then we are really in a good spot because we can really construct a picture of what the event was, what happened, what came out, what was left behind, which elements were created, all of this. Yes?
Where are these two observatories?
Yeah, so LIGO has one observatory in Livingston, and the other one in Hanford. And then Virgo is in Italy. I'm not sure exactly where. It's also down at the moment, so pray for Virgo. IceCube is in Antarctica, I believe. So yeah, you're basically, it is what it sounds like. It's a lot of ice into which we've buried detectors. Yes. Yeah.
Is there any other stars? Because you are mentioning about neutron stars.
Yes. So there's many types of stars. You can have a star like our sun. So that's a very average star. Sorry, it's not a very special star. And so the sun kind of will live on. I'll tell you a little bit more about this actually. Sun's a very typical star, fusing hydrogen, evolving in whatever way. A neutron star is a very special type of object, which is left behind when a supernova happens. And it's a very dramatic thing, like maybe the mass of a sun compressed into the diameter of a city like Davis. You take the sun and you squish it down until it's the size of Davis. And then you have a neutron star. And it's made mostly of neutrons. So it's a strange object, one of the strangest objects in the universe. Sure. Okay. So having worked on this problem for many, many years, what do we know today? This is the periodic table of elements. You may have seen this in your classrooms in chemistry sometime. The different elements are sort of the lightest elements up there, hydrogen, helium, lithium, beryllium, so on, and then the heavier and heavier elements as you go down these rows all the way to uranium. They're grouped in this particular way because of their chemical properties in this table, but what we've done is color-code it with their astrophysical origin sites. So what we now know is that the lightest elements, like hydrogen, were created shortly after the Big Bang. The sort of heavier elements, say your carbon or oxygen or nitrogen, these were forged in stars. As stars evolved and fused hydrogen to helium, then they fused helium to carbon, then they fused carbon to make oxygen, to make silicon, so on and so forth, to heavier elements. Eventually, many stars die in supernova events, these very dramatic explosions that throw out the elements that the star created during its life and create even newer elements in the explosion itself. And so through stars and supernovae, we sort of populate the periodic table, say up to zinc, maybe up to rubidium. maybe up to zirconium. There's uncertainties. Obviously, this is a very broad brush picture that I'm painting in front of you. And then comes the question of the elements that are even heavier. Where do those come from? And it turns out about half and half. They're made in through two different processes, both of which involve capturing neutrons onto a nucleus. These details are not important, but about half and half, they come from low-mass stars, so stars like our sun, and neutron-star mergers, we think, at the moment.
Is this based on evidence you got from multi-message?
Yes. Yeah, so the multi-messenger astronomy was crucial to figuring out the neutron-star merger piece of this. So this is still a very recent thing that we've developed. Before, say, 2015 or so, we were able to detect light and we were able to detect neutrinos, but this neutron-star merger thing only happened in 2017, that we had strong confirmation from multi-messenger astronomy. Yes? So good thing to spot. So those are unstable, and so they don't actually last very long. So that technetium, for example, is created in stars, but there's no stable technetium anywhere, really. It lives for a very short time. So that's why they're grayed out. Another question, yes?
Are the elements missing from here, the man-made elements?
Yes, they are missing, yeah.
Okay.
Yeah.
Do you think it's likely we will discover new elements from these star events that you're talking about?
Yeah, that's a great question. So whether there are even more elements you're asking beyond what's on the periodic table, I would say we're kind of pushing up against nuclear physics at this point. So the elements that are super heavy, transuranic elements, for example, they are very unstable. And so we create them in our accelerators, in our labs, and then they decay away very quickly. So I wouldn't expect to see transuranic elements necessarily in a star somewhere, because first of all, they would have decayed away, and also the quantity might be so little. It's very difficult to observe elements in exact amounts, so there might be so little of it that we'll never see it. Yes?
So do you think all this form sequentially, like first hydrogen, then helium? So
Yeah.
or did the ordering can be
So the timing of it is a great question, and yes. So the question is, did all of this happen very sequentially? First hydrogen formed, then helium, then carbon, then nitrogen, and so on. It is, in a way, sequential, but you can skip elements depending upon nuclear physics considerations. So for example, yes, you need hydrogen to then make helium and then to make lithium, but beryllium and boron have very unstable isotopes that you end up hitting. So you end up hitting this weird area of the chart of nuclides where you're trying to wiggle through and make another element, but you end up basically going from helium in a star, for example, to making carbon. So you fuse 3 helium nuclei and you make carbon. And the way in which beryllium and boron are created is just this completely separate thing. Which actually I should mention. So beryllium, boron, and lithium are a little bit special because much of these elements are created when high energy particles from space slam against molecules of oxygen, not molecules, I apologize, atoms of oxygen and nitrogen in the upper atmosphere. So they just knock out some neutrons and protons from the nucleus and they create new elements. So this is called cosmic ray fission. Okay. So with this periodic table of the origin of elements in mind, we can look at our own bodies and we can think about what we're made of. And so this is a typical composition of a human body. We're mostly carbon, oxygen, hydrogen, nitrogen, smattering of some heavier elements, iodine, zinc, so on. When you look at our cosmic ancestors, about 73% of our body by mass comes from exploding massive stars. Each one of us, 73% of each one of us, comes from exploding massive stars, about 1% from white dwarfs that explode, 16.5% roughly. These are rough. I would not really cling on to the numbers, but that is low mass stars that are dying, stars like our sun. And 9.5% of our bodies can be traced all the way back to the Big Bang, to minutes after the Big Bang when the first elements formed. I think that's incredible. Yes?
How do these proportions compare to, say, like the Earth and our solar system and, say, the galaxy or like the universe as a whole?
Yeah, so the most of the stuff in the universe as a whole is still hydrogen and helium, just because that's what was created right after the Big Bang, and the whole universe was just filled with that. And then carbon and nitrogen. So it's different is the short answer. Yeah, so there's not this much oxygen in the universe. It's mostly hydrogen and helium. Okay, so let's trace that story for a few minutes. Back to the beginning. So the Big Bang happens. The universe is full of soup, particle soup, quarks and gluons fizzing about. As the universe expands and cools, some of these quarks and gluons, they start combining into now subatomic particles like neutrons and protons. And these neutrons and protons begin assembling into nuclei. So one proton is a hydrogen nucleus, two protons is a helium, and along with some neutrons is a helium nucleus, and a little bit of lithium was also made shortly after the Big Bang, but we were not able to create any more elements because basically the universe kept expanding and cooling, and the conditions needed to proceed beyond lithium were not present in the universe, in the early universe. So by the end of this phase of creating new elements, we ended up with a universe full of hydrogen, helium, and a sprinkle of lithium. Don't worry about what exactly this is. This is just showing different isotopes of hydrogen, different isotopes of helium and lithium, and the number of reactions that could be occurring. So if we're trying to understand what happened in the early universe in terms of creating new nuclei, we have to keep track of all of this. The rates at which one nucleus is turning into another nucleus, how they're decaying back into some other nucleus, you have to track all of it, and then you end up with some numbers, some quantitative prediction for how much hydrogen, how much helium, and so on. So already, there's barely anything in the universe, and it's a little complicated to keep track of all of it. And so now you can imagine, as we start making stars, and we start exploding those stars, and then we start taking neutron stars and smashing them together, this is a handful of nuclei. It can get up to, you have to keep track of thousands, 3,000, 4,000 nuclei, and all the ways in which they're connected to each other. So it's not an easy problem. Okay, so the universe is full of hydrogen and helium. From this gas, the first stars formed. We actually don't know a lot about the first stars, and we've never been able to observe them. JWST also probably cannot observe a single star that early in the history of the universe. But we know a lot of things about stars just from studying stars around us. Okay, so when stars are born, say you have a star like our sun. So that's one solar mass. We measure masses and solar masses because things are very heavy in astronomy, and it's hard to keep saying 10 to the 33 power grams and so on. So we measure things in solar masses. If you have a star like our sun, so one solar mass, usually over billions of years, it turns into what's called a red giant. It puffs up. It sheds its outer layers. So this is what's going to happen to the sun. By the way, it's going to swallow us when it puffs up into a red giant. So, it's not going to explode, but it's still not so good for us. But we don't have to worry about that yet. So then you end up with these beautiful nebulas that you might have seen in very gorgeous pictures of these nebulas. And then the core of the star is mostly carbon and oxygen at that point, and it's left behind as this object called a white dwarf. Okay, so that's for the sun. If you have a star that's maybe 10 times the mass of the sun, it undergoes a different type of evolution. So it turns into, again, over millions of years, so the lifetime of a star is proportional inversely to its mass. So the sun's going to live for billions of years. These massive stars, millions of years. Compared to our lives, that's very long, but for a star, that's, live fast, die young, if you're a massive star. So over millions of years, evolves into a red supergiant, maybe a blue supergiant. There's lots of types of supergiants and possible outcomes of stellar evolution. It's a whole field. Eventually, the star will die in a supernova. Maybe the supernova is successful, and you leave a neutron star. The core of the star turns into a neutron star, and you leave that behind. And the rest of the star explodes out into the universe, enriches it with metals. And we see the supernova light curve, we see it go off. Maybe the explosion fails, the star turns into a black hole. Different outcomes are possible when you're a massive star. If you're very, very massive, if you're 80 times the mass of the sun, you're probably not going to be able to explode. This is still an active area of study. So maybe a white dwarf, maybe an explosion. Two rough categories.
How does star form? Is it a gravity force of all the hydrogen get together?
So how does a star form?
Yeah.
So a cloud kind of starts collapsing and heating up, and eventually you can trigger nuclear reactions, and that's the starting point where you can say, okay, now we have a star. But star formation is very complicated and actually not very well understood. So if you have a cloud of gas that's 100 times the mass of the sun, it's not necessarily going to collapse to make a star that's 100 times the mass of the sun. Maybe as it's collapsing, it will break apart into smaller pieces, and then you have lots of stars of different masses. So it's a little bit tricky, but that's the general idea. Yes?
It's maybe not related to it, but I was just curious. When we see a shooting star, have we seen a supernova?
No, so shooting stars are these rocky objects that enter the atmosphere and start burning up. So they're not stars at all. It's a complete misnomer. Yeah. Yeah.
So how big our sun will become a white dwarf? When it becomes a white dwarf, how big the white dwarf will be?
How big is a white dwarf?
Yeah. Let's say around
Oh, yeah. It's about Earth radius. Yeah, it's the size of the Earth. Yeah. So much bigger than a neutron star, but still quite small for. Yeah, a neutron star is like 10 kilometers, 14 kilometers. Yeah. Yeah.
What would the life cycle of that white dwarf be? How much
Yeah.
longer of a lifespan would it have?
So it could just sit there and cool forever, but that actually brings me to my next slide. Sometimes these white dwarfs can explode too. So if the white dwarf has a companion, especially, so if it's a lone white dwarf, maybe it just sits around and cools and cools and cools until it disappears from our view, and it's sad, but it is what it is. But if it has a companion, it can explode. And essentially, there's two possible channels that are typically discussed here, where maybe it's a big star that's the companion of the white dwarf, and the white dwarf is pulling gas from it, and that ends up triggering carbon burning. And burning here always means fusion. When I say burning, I mean fusion. And if carbon fusion is triggered, you can get into this runaway nuclear reaction that blows up the white dwarf. So that can happen by pulling mass from a regular star as a companion. It can also happen when two white dwarfs merge together. So there's different possibilities there. But when a white dwarf explodes, that's called a thermonuclear supernova. When a massive star more than 10 times the mass of our sun, explodes, that explodes in a core collapse supernova, completely different mechanism. In this case, what happens is the core of the star, so this very massive star, 10 solar masses or so, burns hydrogen for a long time, and its core is now mostly made of helium. Then it starts burning helium, core is mostly made of carbon, so on and so forth. And by generating this energy, it's generating pressure to keep itself alive and sustain itself against the pressure of gravity, trying to collapse it. Eventually, the star starts fusing silicon to make iron. Iron is basically the ash of nuclear burning. So at that point, the star runs out of fuel. So suddenly now you have this very massive core and no energy source to keep it alive, to keep it, to sustain it. And so then the core of the star collapses and it sets off the series of events. The core collapses, it bounces, and it sends a shock wave through the star, and that shock wave blows up the star. So it's a different mechanism. It's called a core collapse supernova. So how do we know all this? I'm just telling you a story. We actually do a lot of work to simulate these things. So we take all the ingredients of physics that we need, and we cook up a code that can solve all the relevant equations, and then we put a star in the code, and we let it go. We see what happens. And so this is the simulation of one of these core collapse supernova models going. And so this probably took months to run on supercomputers, because it's actually really, really computationally expensive to do some of these equations that are needed for this kind of calculation. So here you go, your star is exploding, and if you have nuclear reactions that you're tracking in this simulation, you can also say what the composition is of the material that's coming out. Yes? Great question, and that brings me to this slide. Okay, yes, so we have all these predictions from theory for how stars explode. What does the light curve of the supernova look like if the star explodes? What kind of elements are made? Luckily, supernova light curves are something we observe all the time. There's supernova going off very frequently in the universe. Here at Lick, there's this Lick Observatory supernova search that's been tracking supernova for many, many years. So we truly have a lot of data on supernova explosions. Let's see if this actually goes. So we have two things usually. You have how the total amount of light from the supernova goes over time. So it rises and it falls because it's basically a flash of light. And then we take the spectrum. So if we're able to take the spectrum of the supernova, then we can see different elements that were produced in the supernova, for example. And so I talked about the two main classes of supernovae, so thermonuclear supernovae, core collapse supernovae. We know how their spectrum should look based on our predictions. And we can see that, hey, if you see this particular kind of supernova, actually you do see lines corresponding to carbon and corresponding to oxygen and so on. So that's one test. There's a lot of classifications here. These are the observer's classifications. I only have two classifications in my head, and I'm going to stick with those, and that's thermonuclear and core collapse. Okay, we can also look at remnants of supernovae. So say with the Chandra X-ray Observatory, we can look at a supernova that happened a very long time ago, and we can look at what's left behind. And so this is, after a long time, the ejecta from the supernova, the stuff that was thrown out, is kind of expanding, and you can look at it. And you can see that there's silicon and sulfur and calcium and iron that came out of the supernova through X-ray observations in this case. Okay, and this is like locations, this is real data, this isn't something I made up. Okay. Yeah, so supernovae are element factories. I'm going to skip this a little bit. Okay, so we talked about hydrogen, helium, and a dash of lithium. Stars formed, stars exploded. Now we have carbon and nitrogen and oxygen, and we have this iron group of elements, so scandium, titanium, vanadium, all the way up to zinc. Going beyond zinc is a little challenging. And the reason is that at some point, if you have a lot of protons in the nucleus of an element, and you want to push another proton in, both of these particles are positively charged. And it's tough. It's tough to get more and more and more protons to capture on something that's already very positively charged. So you have to be clever about it. So what you can do is you can capture a neutron, and then the neutron decays to make a proton. And then you end up with the next heavier element. So that's the trick. Now this can happen very slowly in a low mass star. You know, there's in the envelope of the star, there's a neutron going along in every once in a while, in a million years, it goes and sticks to some nucleus, and you have the next element. And that's why this is kind of grayed out. About half of the elements that are heavier than zinc are made in this way. But the other half have been, or the other half of these abundances basically has been very challenging to figure out. And so the idea, so basically the way to do that is to capture a lot of neutrons. So in 1 second, let's get a nucleus and let's capture 100 neutrons onto the nucleus and make a very heavy element. So this is a different way of doing it than very slowly over millions of years. Very quickly, 1 second, very fast process. So you need a lot of neutrons. Where can you get a lot of neutrons? A neutron star. Maybe a neutron star is being born, or maybe a neutron star is dying. So these were the two main ideas. Maybe supernova, when a neutron star is born, can make heavy elements, but maybe it's merging neutron stars instead. So if you have a neutron star and you have a companion, over time, their orbits will decay, they'll merge together, and they'll throw material out into the universe, and that material could have a lot of heavy elements. So that's kind of where things sat for a little bit. I already mentioned how weird neutron stars are, so we're going to kind of skip this. So between supernova and neutron star mergers is where the community kept discussing what is the correct answer for a very long time. We also simulated these things, and so you've already seen a supernova simulation. Here's the simulation of 2 neutron stars merging together. So from theory, we know, or we thought that this should work. Okay. In the supernova simulations, it was actually pretty hard to create these heavy elements. As we did more and more sophisticated simulations, we found it harder and harder to create these heavy elements. In neutron star merger simulations, actually, it was pretty easy to produce a lot of material with a lot of neutrons and make very heavy elements. This is a group from the Max Planck Institute in Germany who simulated this. Yeah, so the 2 neutron stars approach each other. Below here is actually the gravitational wave signal corresponding to them. As they approach each other, they start ripping each other apart because of tidal forces. And that's how material gets thrown out into space. There's a question.
Yeah, what's the yellow represent in the inset box? Like it kind of started off with
Yeah.
and then it expanded to a little more.
Let's see here. Oh, yeah, okay. So this is actually a little bit information dense. I think that is the strength of the gravitational wave signal, I want to say. That's rendered in something else. The purple stuff is the stuff that's coming out, the material that's coming out of this merger. And when 2 neutron stars merge together, you can form basically either a neutron star that lives for a short amount of time and then collapses to form a black hole, or you can just immediately go to make a black hole. So there's various outcomes, and it's actually quite complicated to figure out which one is correct.
What was the time duration of that from left to right, backward?
Yeah, so this should actually be probably, my guess would be this is the last seconds of the merger. So the stars start spiraling towards each other in a binary, and it actually takes billions of years for them to get close together to then merge together. But once they're close together, it goes pretty quick. Yeah.
Are the gravitational waves a form of spectrum or type of spectrum, or how are those?
Yeah. So it's actually a laser interferometer that is used to measure the phase difference between gravitational waves arriving on Earth. So I can explain later because I think I have to keep an eye on the time a little bit. But basically, when a gravitational wave passes through the Earth, it'll squish things a little bit in different ways. And that is something that you can measure if you have a laser interferometer. That's squishing. Okay, so theorists are saying, actually, neutron star mergers should make heavy elements. How do we confirm this? Unlike supernovae, which we measure all the time, nobody had seen the light from a neutron star merger until 2017. So in 2017, LIGO and Virgo, that collaboration, measured gravitational waves from a neutron star merger. And so they said, in this region of the sky, we think there's a neutron star merger happening. And immediately, a lot of other telescopes were pointed at that region of sky. And we did it. We caught the light, so it's called a kilonova. It's just less luminous than a supernova. A kilonova signal associated with the neutron star merger. And actually, in terms of how it changed over time, it looked a lot like what people were predicting from the theory side. Okay, so the signal that we saw, the light that we saw, we were not able to identify individual elements in it, but roughly it looked like a ball of heavy elements, radioactively decaying, heating material, and the signal that we saw is the signal corresponding to that heating. So now we have the whole periodic table of elements. Sort of. So this is really, this is very beautiful that we're able to figure all this stuff out when all we can really do is look around in the sky and hope for the best a lot of the time. But the devil is in the details, and that's very much the case in this problem. Because, okay, broad brush, we think this happens and that happens, and this element probably comes from this type of event, but there's so many unanswered questions, even with this neutron star merger discovery. Are neutron star mergers the only way to make heavy elements? We don't know for sure. We can't say for sure that it's the only way the universe makes heavy elements. Maybe there's something else. Maybe there's weird supernovae. Maybe a neutron star being eaten by a black hole. Maybe that's something that could make heavy elements as well. So there's a lot of details that we're hiding behind this pretty picture right now. And those are the details we're digging into. And it's a really exciting time to be doing it. We have the tools to do it. We have this multi-messenger astronomy in our hands, and we also have a lot of data coming in from basically nuclear physics and atomic physics that also goes into figuring out what's going on in a supernova. And yes, so there's many, many fundamental questions that are unanswered. I won't get into every single one of them because I want to give you maybe a few more minutes to ask questions that you have. But this is what I'm working on currently, is establishing the link between theory and observation through very detailed modeling of a supernova or a neutron star merger that has all the pieces of physics that we know go into an event like this: general relativity, neutrino physics, nuclear physics, magnetic fields. And then to be able to do all this, see a signal in the sky. This is actually the light curve of that kilonova. I skipped over it in the interest of time. See a signal like this in the sky, and to be able to say all this together makes sense is a very daunting task. And so we're still working on nailing down all these details. Yes, please go ahead and ask more questions, and then I'll close out. Yes. Yeah.
So, well, I'm just curious. I kind of understand what you're saying, but how does these elements, let's say gold, how does it end up in our Earth?
Thank you for asking that. I should have mentioned. So the idea is this. You have a star that exploded. Whatever came out of it, or a neutron star that merged together, since your specific example was gold, whatever came out of it will mix together with the other gas in the galaxy. Eventually, from that gas, a new generation of stars will be born. And then those stars will go through similar explosions and nucleosynthesis, making new elements, and then it'll mix together again. And so after many generations of stars, you end up with a star like our sun being born, and the planets around it being born. And so the specific structure of the Earth itself is also like geological processes and fractionation. All that is a little bit beyond my particular expertise, but that's the idea, is things mix together, eventually new things are born. Yes?
Have you had a bug in one of your models recently, and so can you talk about it for a moment?
Could you say that again, please?
Have you had a bug in one of your models recently?
A bug?
And so can you talk about it a little?
Yes, there's bugs every day. So let me see what's a fun one. Okay. So when you're coding something up, you have to be very careful about the coordinate system that you're using. And if you're trying to say, take a star and put it on a grid, basically, in a computation, you need to know exactly what's happening in every box of that computation. I'm trying to make sure everybody keeps along. And essentially, I was doing a calculation where I wanted things to, I wanted a funnel of material to go into my simulation in this direction, go in and expand. And I coded it up in such a way that I flipped it, basically. And so instead of something going this way, it was going this way. It's a pretty easy one to fix. Then you're like, oh my God, what was this? Students get better at it too. I don't know what's okay. How's this? Yes.
A follow-up to that, how did you know something was wrong in the first place? It's difficult to find.
Yeah, I mean, you have to be very careful when you're running simulations, of course. Some bugs are more obvious, like if I know I'm trying to put in a funnel of material this way and it comes out this way, something has gone wrong. Other times you might not know that something is wrong at all. If your simulation doesn't break or doesn't collapse in some spectacular fashion, maybe you put a neutron star on a grid and it exploded. Then you know something is wrong. But it is entirely possible to run a simulation and have a completely wrong answer. The way you end up figuring that out is by tracking the physics that you expect to happen very carefully. So you plot every single quantity in the simulation. You do mental checks just in terms of analytically, we have some expectation, if something is expanding, its density should drop, like basic physics things that we know through our intuition and through more pen and paper calculations should bear out. So we always test. You always start out with the simplest possible simulation, You make sure that works. Hopefully there's an analytic answer, an exact answer that you can compare to. And you hope that that works. Okay, then you're sure, then you do 5 or 6 different types of tests in different scenarios. Then you start putting those pieces together. And so that's the way to make sure that you're working in the right direction.
Can everyone join me in thanking our speaker?
Thank you.